So today I'm going to share our recent work, and this is joint work with Yunqi 语博置换景昭, and this work is about how to elicit thinking hierarchy from people. So let me start by asking the audience a question. So we have two circles, a smaller one and a larger one. The radius of the smaller one is 1/3 of the radius of the larger one. And the smaller one rolls around the large one trip back to its starting point. And how many times the smaller one revolves in total? Is any feedback from the chat?
Okay, if anyone has any answers, please you can tape it or just raise the hand if you want to answer. I can't say so fast speaking answering this question, but if anyone has an answer, so go ahead.
Yeah, the audience may be surprised to be asked this math question during a talk. Is any answer?
Yes, okay, we have one answer in chat, 3.
3, yeah. Great, that's the answer I need.
Okay, perfect.
Okay, so we actually asked a lot of Peking University students, and this is the answers we get. So we have, the 3 is actually the plurality answer. Approximately 140 students answer 3. And there is also some answer like 1, 2, 4, 6, and 9. And you may notice that the 3 is basically the ratio between the two radius. And the point is that the correct answer is 4. And I won't explain why the correct answer is 4 because this is not the main point of this talk. My point is that only 16 people answer the correct answer. And how can we know that? How can we identify the correct answer when majority is wrong? And this is the purpose of our research. And this actually studied by some of the previous work. And the question we focus is like, how can we elicit a hierarchy among the answers, where the higher ranking answer may not be supported by the majority, but from more sophisticated people. And the previous one, this math problem, we can see that actually the majority of people make a mistake and only 16 people get it correct. And it can also be applicable to other scenarios, like maybe we ask people's opinions about a philosophy question, and sometimes maybe the majority, they do not provide a very sophisticated answer, and the problem is how we identify this situation. And the idea we have is like, regarding that math problem, so the people who answer 4, they know other people can answer 3 because 3 is like, it's very intuitive answer. But for the people who answer 3, it's difficult for you to know that some people can answer 4. And this asymmetry is the thing we use to build our model. So here we assume that people, they actually have this kind of thinking web. So we use the terminology thinking web because it's like a food web. So basically we kind of think like people, they have different levels of sophistications. And the point is that we think the higher level people, they can actually predict the lower level people thinking, but not vice versa. And this theory is actually, if you're familiar with some behavioral econ stuff, is kind of similar to the bounded rationality theory, but different in this situation. And it's also, I think it's a famous book called Thinking Fast Slow. And that book assumes like hypothesis that people, they have different thinking system, a fast thinking system and a slow thinking system. And the point of our research is we assume that there is this hierarchy relationship between this system. And this is how we use this relationship to identify the hierarchy. So, okay, so the question is how we estimate, how we infer this thinking web without any prior. is like if we have the prior, we definitely know that which answer is the correct answer, which answer is not. But the problem is that in many situations, especially for some field that is very new, and for some like people have very many different opinions, in that case, we actually have very limited prior to know that who is expert, who is not. And this is the situation this work focuses. Okay, so go back to that math problem. So we ask the student this math problem, we ask them their answer, and this is an open response question. So we do not provide them any options. So they just they can answer whatever they want to answer. And the point is, we also ask them, what is your prediction for other people's answer? And in such case, they can actually provide multiple predictions. So for example, for this math problem, like maybe some students, they answer 4, and they predict that other people can answer 1, 2, 3, and they just list 1, 2, 3 in this second blank. And so this is the main trick of this survey, is that we get a matrix, and we call this answer guess, answer prediction matrix. So this matrix actually records how many people answer this answer and predict other people are going to answer that answer. So this is actually the real data for that math problem. So we actually have 100, so the diagonal elements represents how many people answer the answer. So we have 11 students answer 1, 8 students answer 2, 134 students answer 3, and 16 students answer 4, which is the correct answer, but we don't know now. And the point is, for the non-diagonal parts, so it actually means like the 3, not the 13 there, it means that 13 people, they answer 6, and they predict that other people are going to answer 3. And for that, maybe like the 11 above that 13 means that 11 people, they answer 4, and they predict that other people can answer 3. So this is a technical part of this. So any question here? Okay. So we will rearrange after we get people's answers and people's predictions for other people's answer. We get this matrix, and then we're gonna rearrange the rows and the columns together to maximize the sum of the upper triangular area. Okay, so the intuition behind this algorithm is that because we assume that the higher level people, they know what the thinking, they can predict the opinions of the lower level people. So in that case, so if these answers are actually arranged in a perfect order, in that case, we are only they're going to only be positive elements in the upper triangular area. So that is why we use this algorithm. And this is the starting version of that math problem. So we can see that although the answer 4 is only supported by 16 people, but it is the top ranking answer in our algorithm, because among the 16 people, 11 people knows that other people can answer 3. But among the 134 students who answer 3, only 4 of them predict other people answer 4. So this is why we put the 4 as a top ranking answer. And it also actually gives the hierarchy of among all the answers, which is 4, 2, 3, 6, 9, and 1. And 4 is a correct answer. So the point is that our algorithm can identify this correct answer only even is only supported by 16 people, a very few people, and also provides you the hierarchy. And the point is that implementation of this algorithm doesn't require any prior knowledge about the problem. We just get the matrix from people's reports, and we rearrange the rows or columns based on this rule. And we actually get this directed acyclic graph. So I may just skip this part because this is technical. And okay, so this is the full paradigm of this survey. So we ask people, what's your answer? What's the prediction for other people's answer? We get the matrix. We use the algorithm to sort the answers. And then we get this hierarchy. We get this directed graph to represent people's hierarchy. And we actually run this paradigm for studies, and we ask the students some elementary school Olympic math problems. We ask them some Go. Go means board game Go. And we also ask them some general knowledge problem and also the pronunciation of the Chinese characters. And we can see that in all the studies, our average, so this table actually represents the number of questions we get correct. So in all the studies, we beat the plurality vote, especially for the study for Go. So in the Go study, it's like we have 30 problems, and our algorithm actually gets 28 of them correct, while the plurality vote only get, maybe, 23. Okay. Okay, so that is another question. So maybe some of you are familiar with this, but some of you are not. It's just called Monty problem. And so basically there are $3 and there is only the price is only behind $1, and for another $2, there is some like goals behind them. And you make a choice, and then the host gonna like open another for the rest of the $2. The host gonna open $1 and tell you there is a goal behind it. There's no price, and then ask you, do you want to switch? And this is a very famous interview question, and the correct answer is 2/3. But many people answer 0.5 here. And we can see that in using our algorithm, so if we use plurality votes, we're gonna aggregate the answer to half, which is not the correct answer. But if you use our algorithm, you're gonna get the top ranking answer being 2/3, which is the correct answer. And the reason our algorithm put these 2/3 as the top ranking, because among the 34 students who answered 2/3, 26 of them predict other people are gonna answer 0.5. But among the 35 students who answer half, only one of them predict other people are going to answer 2/3. So this is like we get this hierarchy again, and this is another famous problem actually from that book, Thinking Fast, Slow. So in the city, 85% of the taxis are green, the others are blue. And a witness sees a blue taxi, and she is usually correct with probability 80%. And what is the probability the taxi is blue? And for this, I mean, it is like in another like hospital example is like there is a device can tell you whether you have a disease, and this device is correct with 80% probability. And this device says, yes, you have that disease. And what is the probability you really have that disease? So this is this version. And 80 people answer 80%, which is the intuitive answer. And the correct answer is 41%. You need to carefully get it by some Bayesian rule. And the point is that there are also several other answers like 12 and 15 and 20. It's actually very surprised to me and at first. And the thing is, we collect all of these answers and also present this hierarchy and put the correct answer 41 in the top ranking. And the interesting thing is that the most sophisticated answer, 41, is answered by 16 people. And among these 16 people, none of them know that some people can answer 12, 15, or 20. But for the people who answer 80%, and like many of them know that other people can answer. So, I mean, the message from this is like sometimes the most sophisticated level they cannot predict the opinions of the least sophisticated level. But for the middle sophisticated level people, they can actually predict the opinions of the least sophisticated. So this is kind like phenomenon we actually observe not only in this question, but also in many other questions we ask. Okay. So how many minutes do I have?
You have another 11 minutes.
11 minutes. Okay, good. So yeah. So for this boundary river question, we ask people like, what is the boundary river between China and North Korea? And I think like every Chinese knows that the answer is actually Yalujiang is the Yalu River. And we asked the students this question, and we find that 3 students, they actually provide 2 answers, and which is Yalu River and Duman River. And they also predict that other people can only provide a single answer. And it turns out these 3 students are correct. Both of the rivers are the boundary river between China and North Korea. And we can say like, even though like only 3 people get this question correct, and we do not have any prior, we can still identify these 3 people, and also knowing that there is a hierarchy among these answers. So I'm going to skip this one and also this one. Okay. So I think one thing I want to talk about is, when is our algorithm wrong? So our algorithm wrong is that when people can easily guess each other's answer. And this happens when we ask some people something about some dynasty problems in China. And in that case, actually like people, they can easily predict what other people is going to answer, even though they actually don't know what is the correct answer. It's like in the real life, like when people agree to disagree, they perfectly know other people's opinion, but they still stick to their own opinions. In that case, there is no hierarchy, and our algorithm also cannot provide you a good hierarchy there, and the top ranking answer may not be the correct answer. And we also provide, so that is why we provide a measure to measure the hierarchy for the feedback we collect. And we actually find that if the matrix is more hierarchical, our algorithm is more accurate. So basically, our algorithm, our method is applicable in the scenario where people actually do have a very clear hierarchy structure. Okay, so since I only get this, so let me ask you the last question I want to ask is like, why are bar chairs high? Can I get feedback from the audience?
Yeah. Let's ask. This is the open question. So if someone wants to answer, once again, the same, you can text in a chat box or just raise the hand and open your mic and answer.
Do you want to answer this question? Do you have any?
No one hasn't. Frankly speaking, I don't know. I wanted to give some sort of intuitive answer. Okay, the first that comes to my mind, maybe like if someone is short, then this person, in case of the bar chair is high, then it wouldn't feel embarrassed and feel more comfortable sitting on the bar chair. That's the first that comes to my mind.
I see. Yeah, thanks. Yeah. So we actually asked several students at Peking University, and the plurality answer, you actually provide a surprise answer to me, actually. So the plurality answer they provide is because the by country is high, and that is why the chair is high, and we also they also provide many other answers, and we use our algorithm. We ask them like, what is your prediction for other people's opinions? And we use our algorithm to get the hierarchy. And the top ranking answer is that if the bar chairs is high, then you can have a better eye contact with people who stand. So this is the top ranking answer. So the point is for this question is like, I want to say like the idea of our mechanism is not only applicable to this math problem or goal problem. We also want to apply it to this kind of open response problem, and we want to elicit people's opinions. And in that case, we can actually use this one to get a hierarchy where, again, not the plurality answer being the top ranking. And there is also many future work we want to discuss. It's like, I think many of you are not familiar with this area, but I think a natural extension of this is like for all the studies we perform, we just pay people, we just use flat payment. So no matter what they provide, even they provide, I don't know, they're gonna be paid equally. And if we can design a different reward, how can we incentivize them to provide their opinions and predictions for other people's opinions? That's a natural extension. And also it's like for the bar chairs case, one tricky thing here is that if people, they actually provide their open response answer, we need to actually classify their answers at first to run our algorithm. And right now we can only do it by hand. And it is not like the math problem. We can easily classify because, I mean, it's like 0.5 equals half. They're just like different representation for the same answer. It's very easy to run the algorithm automatically there. But for the opinion question is a little bit tricky here. So that is another thing we want to, and also we want to apply this. So the reason we choose like the math goal problems in our study, because these are all the questions with ground truth. And that is why we can validate our answer to compare whether the top ranking answer of our algorithm, it is the correct answer. But we also want to apply it to, like I say, like we want to ask people, we want to elicit people's opinion about some philosophy question. And in that case, we can run our algorithm. But the tricky part is how can we know that our algorithm actually provides you a better hierarchy than just using plurality votes, like which opinion is more popular, and how to actually evaluate our algorithm in that subjective area. I think this is another challenge we want to consider. Okay, and that's a talk. Thanks.